Salam, peace be upon you. My name is Muhammad Laiq Siddiqui, the father of Holophase. Part 19, Book 9.5, Computational Generation, Phi as a Programming Language. Remember the language we are learning. There is one field, Phi, the holophase, one continuous cyclic movement from which all of reality unfolds. When Phi begins to change, its first derivatives appear, and with them, the three dimensions show themselves at once. Time as omega, space as k, and motion as v, built from both. Every higher derivative is a finer question about how phi changes, and each one casts three shadows together: a time shadow, a space shadow, and a motion shadow. These echoes mix and weave into one another, forming the patterns we call fields, particles, bodies, thoughts, and worlds. In this picture, everything that exists is a living tapestry of phi, endlessly echoing through its derivatives and their dimensional shadows. Today, we listen to just one of those echoes. You are stepping across a conceptual frontier in Episode 9, the generative grammar. Our journey has been architecturally magnificent. We built the alphabet and sentences, books 9.1 to 9.3. We discovered the director and the script, the action principle and dynamical grammar that selects which stories are told and how they unfold, complete with immutable conservation laws and vibrant nonlinear interactions, Book 9.4. We have, in essence, a complete theatrical production: stage, actors, script, and director. But today, we ask a meta question that shifts our perspective from theater to machinery. What if the universe is not merely telling a story, but computing it? What if the unfolding of phi is not just a narrative, but a computation, and the laws of physics are not just grammar rules, but program instructions? Today, we enter Book 9.5, Computational Generation. We begin with Part 19, Phi as a Programming Language. We will learn to see the holophase field as the state of a cosmic computer, its derivative rules as instructions, and the flow of time as execution. Our anchor image for this entire book is a vast, intricate clockwork mechanism, an orrery of the cosmos. Imagine a breathtaking machine of gears, levers, and pendulums, occupying a cathedral-sized space. Each gear's position represents a piece of data. The fixed shapes of the gears and the rules of their engagement are the program. As you wind the mainspring, the machine clicks into motion. Gears turn, levers swing, planets modeled on arms begin their orbits. The machine's state evolves deterministically according to its design. It is computing the future positions of the planets from their current ones. The universe, in this view, is such a clockwork, but its gears are made of phi, and its spring is time itself. Today, we learn to read the blueprints. Here is the transformative puzzle of this part. We have developed phi as a language that describes reality. But the description is passive, computation is active. It takes an input, processes it according to rules, and produces an output. Can we reframe the entire dynamical evolution of the phi field, from initial conditions to final state, as such a computation? What is the input? What are the processing rules? And what is the output? And if we can do this, what does it buy us? The answer is a powerful shift in perspective that unifies physics, computer science, and the very notion of generation. Let's build the analogy piece by piece. First, the state. In a computer, the state is the collective configuration of all bits in its memory and registers at a given moment. In the holophase computational model, the state is the complete specification of the phi field and its relevant derivatives over a region of space at a given time. This is the jet of phi which we've encountered before. Not just phi itself, but also its rates of change in time, omega, and space, k, and higher derivatives. This infinite, or very large, set of numbers is the cosmic computer's memory. A localized wave packet is one pattern in this memory. A topological defect is another. Second, the instructions. A computer's processor follows an instruction set: add, load, store, jump. What are the universe's instructions? They are the derivative rules and dynamical equations derived from the actions phi. The fundamental instructions are operations like take the time derivative, apply the operator to, take the spatial gradient, apply the operator dash. Apply a nonlinear function. For example, multiply phi by itself to get phi squared. Propagate, according to the Euler-Lagrange equation, which is itself a compound instruction built from the basic ones. These are not metaphors. In a numerical simulation of physics on a digital computer, this is exactly what the code does. It discretizes space and time, stores phi values in arrays, and at each time step, computes new values by applying finite difference approximations of these very derivative and nonlinear operations. The universe is running the same program, but on a continuous analog substrate. Third, the execution. In a computer, a clock cycle advances the state by executing the next instruction. In the universe, time evolution is execution. Each infinitesimal step forward in time, dt, corresponds to the cosmic processor applying its instruction set to the current state to produce the next state. The program is the entire set of physical laws, and execution is the unfolding of history. So here's the point. The universe is a physical system that continuously updates its state, the phi-field configuration, according to a fixed set of local procedural rules, the laws of physics derived from the action. This is the definition of a computational process. The input is the initial condition phi, t equals 0. The output is the final state, phi, t equals t. The computation is everything that happens in between. Let's explore the triunity of this computational perspective. The time echo of computation, sequential logic, and state transition. Time becomes the sequence of computational steps. The future state is a function of the present state. This is the essence of deterministic computation. The time echo is this logical succession. It frames the arrow of time not just as a thermodynamic gradient, but as the inevitable progression of a calculation from initial data. Each moment is a temporary register holding the results of all previous calculations, ready to be processed into the next. The space echo of computation, parallel processing and local rules. The universe's computation is massively parallel. The update rule, the equation of motion, is applied at every point in space simultaneously. Each location processes its local neighborhood of phi values to compute its own new phi value for the next moment. This is like a cellular automaton, where each cell's new state depends on its own state and its neighbor's states. The space echo is this distributed processing network. The complex global pattern emerges from countless local computations happening in concert. The motion echo of computation, the output as trajectory. What is the output of this computation? For a planet, it's the trajectory, the sequence of positions. For a field, it's the evolved pattern, the spread of a wave, the formation of a shock. The motion echo is the visible dynamic result of the hidden computational process. The orbits we chart, the interference fringes we measure, the particle tracks we observe, these are the printouts of the cosmic computation. Now let's locate this paradigm-shifting node on the master tree. We are at the root of Book 9.5, Computational Generation, an entirely new trunk growing from the core of Episode 9. This node, phi as a programming language, depends on everything that came before. We need the alphabet, derivatives, the sentences, waves, fields, and the dynamical grammar, equations of motion, to have a complete instruction set. It enables the breathtaking ideas that follow in this book. Understanding the universe as a cellular automaton, exploring algorithmic information and novelty, and ultimately, seeing complexity as the product of simple programs running on the substrate of phi. To ground this cosmic scale computing concept, let's light our lanterns across scales of engineered and natural computation. A near lantern from everyday technology, a spreadsheet recalculating. Imagine a massive financial spreadsheet. Each cell contains a number or a formula. The state of the spreadsheet is the value in every cell. The formulas are the physical laws. They dictate how a cell's value depends on others. For example, this cell equals the sum of those 5 cells. When you change one input value and hit recalculate, the spreadsheet executes. It looks at all formulas, computes new values based on dependencies, and updates the entire sheet. This is a perfect analogy. The phi field is the entire spreadsheet grid. The formulas are the derivative and nonlinear rules. Time evolution is the recalculation. A wave propagating is like a change in one cell, triggering a cascade of updates across a row according to the formula of the wave equation. A middle lantern, from computer engineering. A field programmable gate array, FPGA. An FPGA is a chip whose internal logic connections can be reprogrammed after manufacturing. You configure it by specifying how each tiny logic block should function and how they are wired together. Once configured and powered, the chip computes. Signals propagate through the designed network of logic gates, transforming inputs to outputs. Now imagine the fabric of space-time as the ultimate FPGA. The configuration is the action SFA. It sets the wiring and gate functions, the laws. The power is the initial energy. The signals propagating are the evolving patterns in the phi field. The FPGA computes in discrete time steps. The universe computes in continuous time, but the conceptual parallel is exact. A far lantern from quantum computing, a topological quantum computer. This is a cutting-edge proposal where the physical qubits are non-abelian anyons, the very topological defects we studied in Book 9.2. Their world lines are braided in spacetime. The braiding pattern performs a quantum computation. It transforms the quantum state of the anyons in a way that is topologically protected from small errors. Here, the computation is performed directly by the dynamics of topological defects in a phi-like field, the fractional quantum Hall fluid. The program is the braiding sequence. The output is the final quantum state, read out by interference measurements. This is not an analogy. It is a literal physical embodiment of the idea that the universe's dynamics are a computation, and we can harness a piece of the universe to perform computations for us. From spreadsheet recalc to FPGA operation to topological quantum computation, the theme is unmistakable. Information processing is a physical process governed by local update rules. The universe is the supreme physical instantiation of this principle. Its state evolves by processing itself according to its own built-in code. What then is the specific language role of viewing phi as a programming language? It is the interpretive frame of execution. It is the perspective that treats the entire generative grammar not just as a declarative description, this is what happens, but as a procedural specification. This is how to make it happen. It answers, if we wanted to simulate or generate the universe from scratch, what algorithm would we run? The Holophase answer is, run the algorithm defined by the derivative rules and nonlinear interactions of phi. The core question this part asks about phi is, can the entire time evolution of the phi field be reinterpreted as the execution of a computational algorithm where the field's configuration is the data state and the physical laws are the processing instructions? And what are the basic opcodes of this cosmic processor? We are moving from seeing phi as a description to seeing it as an engine. What does this computational viewpoint do for our understanding? It unifies physics and computer science, suggesting physical laws are a kind of natural software. It provides a powerful framework for simulation and prediction. To know the future is to run the computation. It opens the door to asking profound questions about the complexity, compressibility, and intrinsic information content of physical states. It suggests that novelty and complexity in the universe are the products of simple programs running on rich initial data. Now, stability and breakdown. The computational perspective is conceptually robust for deterministic classical physics. It holds perfectly for systems described by well-defined differential equations. It breaks down or becomes subtle in two domains. Quantum mechanics, where the state is a probability amplitude and evolution is unitary, still computational, but in a Hilbert space. Truly stochastic or non-algorithmic processes, if any, exist. The claim is not that every physical detail is computable by a finite human program, chaos theory forbids that in practice, but that the universe's own evolution is its own computation. The mapping is exact. This brings us to our empirical anchor, falsifiability. The claim that physical processes can be mapped to computational operations on phi patterns is not a vague philosophical stance. It's a concrete methodological hypothesis with testable implications for engineered computing devices. The central claim. For any physically realized computing device, whether a silicon chip, an optical computer, a DNA computer, or a quantum annealer, its logical operation must be implementable by configuring a suitable phi field, or multiple interacting phi fields, in an appropriate medium and letting it evolve according to the dynamical laws of that medium. The performance metrics of the device, gate speeds, error rates, power dissipation, must be predictable from the phi dynamics of the underlying medium, without needing to postulate new, non-physical logical forces. Concrete measurement scene, an all-optical logic gate. We construct a computing element using only lasers and nonlinear optical materials, for example, a crystal with a strong second-order nonlinearity. The goal is to implement a fundamental logic operation, like an AND gate. Two input laser beams, representing bits, on equals 1, off equals 0, are combined in the nonlinear crystal. Due to the nonlinear interaction, for example, some frequency generation, a third output beam is produced only when both input beams are present at high intensity. This output beam is the logical AND. We characterize this gate. We measure its truth table, output intensity for all four input combinations, its switching speed, how fast the output turns on/off, and its error rate due to noise, imperfect alignment. The pass condition, validation. The operation of the gate is fully explained by the nonlinear wave equations, derived from an action S for the electromagnetic field in that crystal, governing the three interacting light fields, the two inputs and the output. The measured truth table, switching speed, and error rates match the predictions of these equations when fed with the measured input beam properties, power, wavelength, shape. We can point to specific terms in the phi-based model, for example, a chi2 nonlinear coupling term, and say, this term is the AND instruction. The physical computation is directly mapped to a phi interaction. The fail condition, falsification. The gate works as a logical AND, but its behavior deviates systematically from the predictions of the nonlinear optical equations. Perhaps it works at input powers orders of magnitude lower than predicted, or its output exists in a stable state not allowed by the equations. If, to model its function, we must add ad hoc terms to the phi dynamics that have no other independent physical justification, then the claim that standard phi dynamics can implement computation is weakened for that system. If we discovered a class of robust, high-speed computational devices whose operation could not be modeled by any known phi-based dynamics in any known or plausible material, it would challenge the universality of the phi as computation view. It would hint at physics outside our grammar. This falsifiability ensures our computational perspective remains tied to the gritty reality of engineering and device physics. Let's cultivate a practical recognition skill. You can train your mind to see computational logic in any dynamical system where the future state is determined by the present state according to fixed rules, especially if those rules are local and can be seen as processing information. Watch a game of Conway's Game of Life on a screen. This is the canonical cellular automaton. Each pixel's next state, on, off, is determined by a simple rule based on its current state and its 8 neighbors. The evolving patterns, gliders, oscillators, complex structures, are the output of a computation where the initial pattern is the input and the local rule is the program. The universe, in this view, is a continuous, massively high-dimensional version of this. Observe a domino rally. You set up a complex chain of dominoes, initial state. The rule is, if a domino is tipped past a certain angle, it falls and strikes its neighbors. When you tip the first domino, the computation executes. The final pattern of fallen dominoes is the output. The rule is local and mechanical. Consider the neural activity of a simple organism. Sensory inputs trigger patterns of neural firing, state changes, according to the fixed wiring and biochemical rules of the neural network. The organism's subsequent action, moving toward food, away from danger, is the output of this biological computation. The program is encoded in its genetics and development. Whenever you see a system where what happens next is determined by what is now via clear, repeatable rules, you are looking at a computer. The universe is the grandest example. We must connect this computational leap deeply to our Holophase journey. In previous books, we built up the what and the why of the story. Now we are articulating the how at the most fundamental mechanistic level. The generative grammar is the source code. The universe is the runtime environment. Execution is reality. We haven't added a soul or a programmer. We've simply recognized that the structure we've already deduced has all the hallmarks of a computational process. This is a profound validation of the internal coherence of the Holophase framework. If you want to see the full mathematical derivations and exact equations behind this idea, the formal mapping between differential operators and computational instructions, the discretization schemes that link continuous physics to discrete algorithms, the information theoretic treatment of field states, you can search for Holophase on Zenodo. There you will find the scientific papers that this audio journey is built on. Let us pause and feel the expansion of our vista. With the opening of Book 9.5, we are no longer just reading the universe's book. We are studying its operating system. We have moved from linguistics to computer science. This perspective empowers us to ask new, thrilling questions. How complex is a given phi pattern? Can the laws be compressed? What is the universe's algorithmic information content? Could different initial conditions run different programs? In the next part, we will dive into one of the most concrete manifestations of this idea: cellular automata and emergent computation. We will see how simple, discrete local rules on a grid, a drastic simplification of the continuous phi field, can nonetheless generate astonishing complexity, mimic physical phenomena, and even become universal computers. This will strengthen the intuition that our continuous universe could indeed be the limit of an unimaginably fine-grained cellular automaton, with phi as its state variable. Before we end, the mandatory zoom out to hold our scope. The computational view adds no new substance. The program is the actions phi and the derivative rules. The data is the phi field and its jet. The execution is time evolution. We are merely using a new metaphor, the computation metaphor, to describe the same generative grammar. But a powerful metaphor is a lens that reveals new landscapes. One field, phi, plus its infinite tower of derivative questions, executing the algorithm of its own dynamics. From this computation, all things are printed out. As we conclude, hold the image of the cosmic orrery, the clockwork universe. Each gear is a local value of phi. Their interlocking teeth are the derivative rules. The steady turn of the mainspring is the flow of time. The moving model planets are the emergent patterns, the galaxies, the cells, the thoughts, that arise from the relentless, local, mechanical computation of the whole. We are not just observers of this machine. We are transient, self-aware patterns within its endless calculation. The universe is not merely written in phi, it is continuously computing itself in phi. And we are learning to read the source code. Salam and peace be upon you.